Yeah, so today I'll be talking about the work that my group has focused on the past few years, which is to try to quantify the radiative forcing of desert dust, in part because that's really been overlooked, I think, by climate assessments, including the latest assessment report from the Intergovernmental Panel on Climate Change, or IPCC. And the really critical context for all this, as you're probably aware, is of course climate change, and climate change more specifically being kind of this battle between warming from greenhouse gases and cooling from aerosols, right? And that balance between the two, and the aerosol cooling offsetting some of the greenhouse warming, is really critical if you think of where we are in this moment in time. The world has already warmed 1.4 degrees centigrade, really picked up the past few years. So we're very close to the 1.5 degrees, which we're no doubt going through, we're going to pass through, and we're headed for the 2 degrees threshold. And if you see here, this is the curve of the warming we've had over the past 2 centuries or so. The black line is the total anthropogenic warming, and you can see there's the various greenhouse gases here. Let me see if I can show my pointer actually. Pointer options. Yes, that's here. Okay. Various greenhouse gases, and then that warming, of course, has been offset by cooling from the increase in aerosols, particularly sulfate, both through direct interactions, scattering predominantly of solar radiation, and interactions with clouds. And so just how much this offset has been of the greenhouse warming by aerosol cooling is really critical for predicting what will happen in the future. Now, as an illustration of that, okay, sorry, now the pointer, because the pointer doesn't work anymore. Let's see. Next. Okay. Okay. As an illustration of that, if you imagine that in the past we actually did not have any aerosol cooling, right? That means that this 1.4 degrees of warming we've had is because of greenhouse gases. So in other words, the greenhouse gases have added 1.4 degrees centigrade of warming. Versus, if we did have a lot of aerosol cooling, say greenhouse warming had been offset by 1 degree, that means that greenhouse warming actually warmed by 2.4 degrees, right? So that'd be in that case, the climate would be a lot more sensitive to greenhouse gases. And so we would expect in the future, as greenhouse gases keep accumulating and the aerosol load does not increase or probably decrease, that we'd have very high climate sensitivity. We would have a lot of warming. So how much aerosol cooling has been in the past is very predictive of how much warming we're going to see in the future. This was really nicely summed up in a paper already 2 decades ago by Maimrad Andre, basically simulating out the future with and without aerosol cooling, so with and without a past warming that was partially offset by aerosol cooling. And you can see there's a really large difference between those futures. There's about a factor of 3 in the predicted warming by the end of the century. Of course, this range has come down because we've constrained the aerosol cooling more since 2 decades ago, but the same principle stands. It's really critical for understanding what has happened in terms of aerosol cooling in the past in order to be able to predict the future warming that we're going to get. Now, I know this is the Dust Doctoral Network, but I still want to show this really cool video of the different aerosol species on our planet. The green here you can see from the biosphere. These are organic aerosols. Up here, the blue are sea salt aerosols. They're whipped up by strong winds across the oceans. The white are sulfate aerosols from polluted regions, and of course, the swirling masses of orange is dust. What we will focus on, emitted here from the world's deserts. Beautiful swirling masses. But this dust has actually been omitted from climate assessment. So this is from the most recent assessment report, summarizing the perturbation to Earth's radiation budget by different climate forces. And at the top here, of course, we have the greenhouse gases, carbon dioxide, methane, nitrous oxide, and so forth. And then towards the bottom, we have the aerosol species, sulfate being the most important, but also organic carbon, black carbon, and ammonia, black carbon being the sole warming aerosol. And that change in the radiation budget has produced a change in the surface temperature, the global surface air temperature, or GSAT, that's corresponding to the radiative forcing. You can see that the uncertainties in the perturbation to the energy budget are mostly in the aerosols, right? That's where the uncertainties are. We know relatively well what carbon dioxide does. But what's missing here, of course, is dust. We have these 4 aerosol species, but dust is not in this graph. And why is that? Why has dust been omitted from these assessment reports? There's 2 big reasons for this. One is that when you simulate dust in the climate model from the pre-industrial period to the present day, it's not very exciting. Nothing really happens. This is from 6 CMIP6 models, CMIP6 standing for the Climate Model Intercomparison Project. And you can see that these 12 models, basically there's wiggles up, but they always go down. And so there's no secular trend in these 12 models. So there's nothing really happening with dust in these climate models over time. So that's one reason it's not considered as a forcer for the global energy budget. The second one is that dust is, at least most dust, is a natural aerosol, being emitted by wind, blowing over bare soils. And therefore it's often considered a climate feedback. So something that responds to the climate being changed, because that change in climate can change the wind, it can change vegetation cover by changes in rainfall and temperature, and therefore it's not considered an anthropogenic radiative forcing. But of course, I would argue that that is incorrect because we know that human actions have impacted dust emissions through a large number of ways. Perhaps one of the most important ones is the diversion of surface water flows. This was from a really nice paper in Science a few years ago. And so the circles on this map represent all the lakes in the world. And if it's red, it has shrunk. And if it's blue, it has grown. And you can see this is mostly red. And it's red especially near arid regions where there's bigger demand for surface water. And this has caused a drying of lakes across arid regions. The most famous of this is probably the Aral Sea, which used to be much bigger than it is today and has turned the now dry area into a prolific dust source in Central Asia. We also have lots of examples of these in the United States. Owens Lake used to be the biggest dust source in California before lawsuits by citizens affected by the dust due to health issues forced the state to mitigate these emissions. There's a Great Salt Lake in Utah that's drying out. The Salton Sea also in California. All these lakes are drying out and turning into dust sources. There's our agriculture that also can greatly increase the emission of dust through a few different ways. One is the direct disturbance of soils versus by plowing, and also things like tractors driving over it, although that's thought to be a smaller source. And another way is through the removal of vegetation, especially in more marginal agricultural regions, through grazing, goats, for instance, and the trampling of soils and that destroying fragile crust, biological, physical crust that keep the soil from blowing. And the third really critical way in which we have affected dust is through this feedback. So, for instance, increasing drought in certain regions, especially the US Southwest, for instance, has gotten drier and is expected to get drier under climate change, could drive an increase in dust as well. Of course, we can't tell what is feedback and what is forcing in this case. But we do have all these reasons to believe that dust has increased, and we see this in deposition records. So this is from a really nice paper by Hooper and Marks in 2018. They compiled all these records of deposition. So these would be things like ice cores or marine sediments, where we can measure fluxes of dust. And these are all the sediment cores that are thought to be measuring long-range transported dust, or not very local dust, that's indicative of a larger source region, say. And you can see of all these deposition records, they calculated what the flux is in the pre-industrial period. This is the red circle. This is normalized to 1. And then what the flux is in the modern period. These are the colored circles around there. And you can see that for almost all of these cores, the colored circle is larger than the black circle, meaning that there's been an increase in dust since pre-industrial times. And there's one particularly dramatic core, None of the other ones are this dramatic, but this is off the coast of the Western Sahel. And this was published in Nature by Mulitsa in 2010. And you can see there's this tremendous increase in dust deposition there. That seems to be in the especially rapid rise here seems to be correlated or seems to be happening at the same time as industrialized agriculture in the region. So that's the hypothesis made in that paper, that that's what's driving this increase. But of course, we don't really know. Now, if we now simulate the deposition flux in that grid box by different models, this is from the same compilation of CMIP6. And these are the models that reported the deposition fluxes. So it's a subset of those models. And you can see none of those models even remotely capture this trend. So we know from the deposition records, dust is increasing. We expect this from our basic understanding of dust, but we are not seeing this in climate models. And therefore, it is not in our current assessments of how climate has changed, how the energy budget has changed, how that has driven changes in temperature, and this in turn informs or constrains the climate sensitivity. So my objective for this talk is to add dust in the hopes that for AR7 it will actually be put in. So quantify the radiative forcing that is produced by the change in dust, and from that get the change in temperature. So to do that, we're going to answer three central questions. The first one, of course, how much has dust loading actually increased since pre-industrial times? And then once we do that, we need to be able to account for this in models. So second question, how can we account for historical dust changes in models? And then once we have it in models, we can figure out, okay, what has been the direct radiative forcing produced by changes in historical dust? And for that, the direct radiative forcing means interactions with shortwave radiation, which has been lots and lots of work on, and interactions with longwave radiation, which has been relatively overlooked. I'm going to spend a lot of time figuring out exactly what the radiative forcing due to dust interacting with longwave radiation is, because that dust essentially acts as a greenhouse gas in the longwave spectrum. So we're going to go back through that compilation I showed you. So we pulled those records from that paper, discarded a few that we deemed to be due to local dust, and then added a few new ones that were published since then or that were overlooked by that paper. And we end up with 19 different deposition records across the world. We have a fair number in Greenland, in Antarctica, in the Himalayas. These are all ice core records. We have some marine cores. We have some cores from coral. We also have actually an ice core in the Alps. We have some lake cores, so it spans the spectrum of sedimentary records. We have those 19 deposition records. We're then going to combine that with the DustCom data set that my group has produced over the past few years. This is essentially a reanalysis product or climatology, I should say, for modern dust, including things like size distribution and extinction efficiency. And this constrains the relative contributions of different source regions of 7 different source regions to the global dust cycle. So including the contribution of each source region to each of these deposition cores. You see that in this map. So the colors represent the dominant source region for each grid box. And so, for instance, for core, let's say here in Greenland, that's nice and interesting. Here we see that there's, say, 50% of dust coming from North Africa, 30% from North America, and 20% from East Asia, something like that. So we're able to quantify the relative contribution of each source region to each deposition core with uncertainties in how this that are propagated from the building blocks of this DustCom data sets, which include satellite data, an ensemble of model simulations, and AirNet data. So what we do then is we combine those pieces of information. So we have those 19 dust deposition records. We now have the fractional contribution of these 7 source regions to each deposition core in the modern climate. And then we figure out, okay, what is statistically the most likely way that these 7 source regions varied over time in order to produce these 19 dust deposition records. So the time series in these 19 deposition records, just from minimizing the disagreement against those 19 deposition records. And so from that, we get the temporal evolution of each source region. And here is the results from North Africa. This is done using a bootstrap procedure, propagating all the uncertainties that we can quantify. That's why there's a fairly large uncertainty range here. But this method also needs to make some assumptions for which we cannot quantify the error. And one of the critical assumptions is that changes in deposition rates at these deposition cores are driven by changes in emissions in source regions rather than changes in transport, for instance, or changes in the deposition where the dust is being deposited from the atmosphere. That's a very critical assumption that we need to make in order to get a result out of this. But it makes it uncertain. Now, just to highlight how this method works for the most important source region, North Africa, this is the source of about half of the world's dust in the modern climate. North Africa is very interesting because we have 4 cores that are dominated by North African dust, and then we have a few more cores that are influenced by it, but 4 that are really dominated by it. There's the one that I already showed you. There's an ice core here in the Alps. There's a lake in Corsica right next to it, at least on the map perspective. And there's this core here in the Bahamas, from a coral record. And the interesting thing here is that 2 of these cores, the record that I showed you and the record in the Alps, show a very strong increase in dust, but the 2 other cores do not. They show pretty much a flat trend. And of course, we don't know which of these cores is right. It might be that some of them are wrong and some of them are right. It might be that all of them are right, that they're receiving dust from different reasons. We simply don't know. But what the method does is it draws with replacement these 19 cores. So it uses a bootstrap procedure, and for each iteration of this bootstrap procedure, it draws 19 cores with replacement. And so for each iteration, it can either draw only cores for which the trend is flat, only cores that show a strong increase, or most likely a combination of those 2. And so what comes out of this method then spans that range of probabilities. So we're finding that the African dust increase has been between basically flat and 100% increase since the pre-industrial period, with, of course, the most likely result being intermediate between those sort of extreme bounds. So that's where a large part of where these error bars come from. So, okay, we find about, on average, the median result, about a 50% increase in African dust. For Asian dust, which accounts for another, say, 40% of global dust, so coming especially from Central Asia and Eastern Asia and the Middle East, did we see an even larger increase, especially, for instance, in the ice cores in the Himalayas, about 75%. And then for the southern hemisphere, the signal is a little bit less. There's more variance in the deposition records there, and we also have less data there, but we still see around a 30% increase in dust there, but with larger errors. Now, the interesting thing is, one of the interesting things here is that there's a peak in the 80s in both Asian dust and African dust, and that lines up with independent data, like visibility records, the Barbados a dust record that goes back to the 60s. And the fact that we see a larger increase in Asian dust roughly aligns with the much larger anthropogenic land use changes in Asia than in northern Africa. So if we add all this up now from the changes from the different source regions, we find that global dust loading has increased by around 50%, so 55 plus or minus 30%. And that's kind of a big deal because dust accounts for about a quarter of the extinction of solar radiation by aerosols. It's the main nucleator of ice crystals in mixed phase and cirrus clouds. It delivers important nutrients to ecosystems, and that increase is not in current climate models, right? This is the graph I showed you before with these 12 CMIP6 models being flat. They have essentially no secular trend, and completely missing this increase in dust that we know is there from the deposition records and that we expect is there from our basic understanding of how human actions have increased dust emissions. Okay, so we've answered this first question then. We think dust has increased by around 50% or so, plus or minus 30%. That's great, but in order to get this into predictions for climate change, right, we need to get it into models. So how can we account for this historical change in dust in models? So let me go back to this method, right? So we combine these 19 dust deposition records with the DustCom data set, and from that we can actually invert and get where the emissions are coming from and how they have changed over time. So we get a dust emission inventory, meaning that we get for each grid box season and each decade, we get the flux of dust that's being emitted. And then we have many ensemble members through this bootstrap iteration, so we can put errors on this. And from that, of course, we get a large increase commensurate with this 55% or so global increase. We get a similar increase in the global dust emissions because the deposition processes haven't changed all that much. So we have to test that this works. We have implemented this into the community Earth system model, which is sort of the default model, climate model in the United States, because it's a community model, so we all have access to it, can modify the code and so forth. And we can see that this increase in emissions, of course, has increased the dust aerosol optical depth. So that's approximately the average number of times that a photon coming from the sun will interact with a dust particle. So this was around 0.02 in the pre-industrial period, meaning around 2% of photons would be scattered or absorbed by dust, and now it's 0.034 or so, meaning around 3.5% of photons are interacted with by dust in the present climate. So a large increase, and this is also driven an increase in radiative forcing, which I'll get to. We want to check, of course, that this dust emission inventory does what we think it does. This is the similar to what I showed you before. This is time on the x-axis versus the dust aerosol optical depth change relative to the pre-industrial baseline. The black here is what's reconstructed from DustCom. The blue is actually a paper from my group, led by my former student Danny Lung, who's now at NCAR, who developed this really nice new dust emission, physically based dust emission parameterization, and even that got pretty much a flat response. So there's still really things missing in the link between climate and dust emissions in models. And then all these lines are from the different CMIP6, both the historical and the AMIP. So the ones with reconstructed sea surface temperatures run. So none of those runs can reproduce the increase in dust, which now the dust aerosol emission inventory can, right? So if we put that into a CSM2, the red line, we are now able to reproduce this historical trend. Okay, so that brings us then, now we've determined how dust loading has changed. We've developed the tool for putting this into models. So now we're ready to figure out, okay, what has been the direct radiative forcing produced by historical dust changes. And I want to spend some time on really focusing on the long wave component as well. But first is we started this experiment AeroCom being this collaboration across different climate modeling groups, essentially, with different aerosol models. And we started this new experiment for which we got 8 models across the world to participate, the dust radiative forcing or DRF experiment. So we have these 8 models, and these 8 models ran 4 different simulations from 1850 through 2000, with sea surface temperatures from coupled runs by the same model. So these runs only use the aerosol components of the atmospheric components of the models. The first one being the HIST SST. This is straight from the CMIP6 protocol. This is our base case. The only thing we changed is that we force models to have a dust aerosol optical depth in the modern period to be within observational bounds. And that observational bound is around 0.03 plus or minus 0.01 from a paper by Dave Ridley about a decade ago now. But the models do their run as normal with their normal dust parameterization. We just include scaling constants to force the dust optical depth to be around 0.03 in the modern climate. Then we have 3 different simulations that use, in some form or another, the dust emission inventory or dust emission reconstruction. First, we have dust SPT, standing for dust spatial. And these read in directly the reconstructed emissions per grid box and per season and decadally varying, right? That's why you see the steps here. Then there's dust GLB, standing for dust global. here the model dust emissions are scaled by a global factor to match the reconstructed global trend. So the models use their own dust emission parameterization, but they include a scaling constant, and the scaling constant varies every decade in order to match the dust reconstruction. And then there's dust GLB with pre-industrial aerosols, the third one here. So it's the same as the dust global simulation, but now we keep the anthropogenic aerosols at their pre-industrial level. So we can tease apart the radiative effects of the increase in dust and the increase in anthropogenic aerosols. Okay. Here are the results from these 8 different models. And of course, you'll see there's a range, but clear trends. So on the left is the direct radiative forcing from anthropogenic aerosols, the different models, and a median forcing of around -0.2 to -0.1 watts per square meter. And in the middle here is the effect of dust aerosols, which we see somewhat surprisingly is of the same magnitude as that of the anthropogenic aerosols. And mind you, these are just the direct radiative forcing, so no cloud effects. So for both the anthropogenic and the dust aerosols, the end of the 20th century direct radiative forcing, the range by the models is between around -0.3 and +0.1, and the warming here is caused by strong warming from black carbon in some of these models for the anthropogenic aerosols and for very absorbing dust. And so the contribution of dust is, in terms of radiative forcing, is similar to that of the anthropogenic aerosols. And so if models would now include the effects of dust, it would double the direct radiative forcing due to aerosols. So quite an important impact. But if we dig into this a little bit deeper, there's some limitations with these models that we really ought to be accounting for. And the most important one of these, I would argue, is the limitation due to the interactions with long-wave radiation. Because on the left here is the radiative forcing due to changes in the dust interactions with shortwave radiation, or changes in the dust direct radiative effect with shortwave radiation. And that looks a lot like the net, and that's because the models simulate almost no radiative forcing from changes in dust interactions with long-wave radiation. And is that realistic? Well, probably not, because we know models are not good at getting dust interactions with long-wave radiation for 2 main reasons. The most important one being that most models omit, with one exception that I'm aware of, most models omit the effect of dust on long-wave radiation through scattering, which is probably quite important. It's a really nice paper by Jean-Louis Dufresne pointed this out 2 decades ago. And we know that most of these models underestimate the abundance of coarse dust, dust larger than 2.5, but especially larger than 10 microns. And it's especially this very coarse dust that is effective at interacting with long-wave radiation, because long-wave radiation has a wavelength of the order of 10 microns or so. So you need a dust particle that's of similar size to interact with it. That's why only dust really interacts with long-wave radiation and not other aerosol species, which are much finer. So, okay, we're not going to believe what the models tell us here then about what the dust long-wave direct radiative forcing is because of these limitations. And instead, we're going to use observations and this dustcom data set, this constraint on a modern day dust climate, to really determine what is the long-wave dust direct radiative effect and the forcing. And here I should explain the direct radiative effect is the effect of dust on the radiation budget. So if you took dust out of the Earth system completely, what would be the change in the radiation budget? And the forcing, the dust radiative forcing, is the change in that direct radiative effect, right? So about a third of the dust in the present climate is new since pre-industrial, right? From that 50% increase. So it means the dust radiative effect has also increased by that third, and the dust radiative forcing is that difference between the pre-industrial and the modern period. Okay. But why then is there a long-wave direct radiative effect? How does dust generate this? So I have some schematics to illustrate that. The left here is the atmosphere without dust. Each of these red arrows represents radiation in the long-wave spectrum and specifically in the atmospheric window. This region of around 8 to 13 microns in our atmosphere that's relatively transparent to radiation, and where radiation leaving the surface, most of that makes it to outer space. Outside of that window, that radiation emitted by the surface is absorbed within the Earth system, usually by water vapor, but also by ozone, carbon dioxide, other greenhouse gases. So most of that radiation makes it to outer space here. If we now add dust, the situation is quite different, because dust, being so coarse, it interacts effectively with long-wave radiation. It does so, about half of these interactions are scattering. So dust scatters this radiation, and around 15% of the scattering interactions result in the radiation that's traveling upwards being scattered downwards, and that thus affecting the outgoing long-wave radiation and therefore the Earth's radiation budget. And of course, then there's absorption. So the rest of the radiation here will be predominantly absorbed. And because of Kirchhoff's law, if a substance is absorbing at a particular wavelength, it must also be emitting at that wavelength. So not only does the dust absorb the long-wave radiation coming from the surface, it then emits its own radiation, but it does so with a lower temperature, a lower brightness temperature, because it's higher in the atmosphere and therefore colder. And so the radiation that's coming out of the dust layer is going to be of a lower intensity than it's receiving from the surface. So there's less coming out here. And then there's absorption again by the atmosphere above the dust layer, further reducing the outgoing long-wave radiation. So that's how dust exerts a top of atmosphere radiative effect. So how strong is this? We can tell relatively well from satellite data and from aircraft data, because you can measure, what is the long wave flux. You can measure what is the optical depth of dust, and you can figure out what the relation is between those. Then correcting for things like changes in water vapor content. And there's been a bunch of studies that have done this. I've plotted them all on this graph here. So what these show are the direct radiative effect efficiency. So this is the change in the outgoing long-wave radiation per unit of shortwave optical depth. So per unit of optical depth in the shortwave spectrum. And that's in the shortwave spectrum because that's where we can measure, where we have really good measurements of optical depth from both ground-based and satellite data. So this direct radiative effect efficiency is a way to normalize the perturbation to the outgoing long-wave radiation by the amount of dust that's in the atmosphere. And these observational estimates show that this perturbation in the outgoing long-wave radiation is around 10 to 20 watts per square meter per unit of shortwave dust optical depth. And this is averaged over a diurnal cycle. And that's quite striking, that there's such a fairly narrow range, right? It's only about a factor of 2 dynamic range here. So that already implies that we can probably constrain the perturbation of the outgoing long-wave radiation due to dust globally relatively well, because the observational data is, really well behaved, I would say. Okay, but what do models do then? I have a compilation of 6 different models that simulated the interactions with long-wave radiation, including the long-wave direct radiative effect efficiency. This is of these 6 models. This is This is a middle of the road model in terms of agreement with these measurements. This is the Monarch model out of the Barcelona supercomputing center. And you can see this model greatly underestimates the observational constraint. It has a much lower direct radiative effect efficiency than shown by measurements, by observations. This is the top here is in the spring, the bottom is in the summer, and we can see the same thing. If we now put this on a scatter plot, separated here also by the in situ data from aircraft satellite data, as squares, and the in situ data, these circles are from aircraft campaigns. And you can see, the model greatly underestimates by about a factor of 2 the observational constraints. If you now look at all these 6 models we have in this ensemble, they all show pretty much the same thing with some variability, but pretty much they're all greatly underestimate the direct radiative effect efficiency. Now, why is that? Why do models consistently underestimate the long-wave dust direct radiative effect? Well, the left here is what's happening in the real world, right? This is what models do. Models don't account for long-wave scattering. They miss almost all the supercoarse dust with a diameter larger than 10 microns. And so the cartoon for models looks more like this. There's no scattering. A lot of the coarse dust that's effective at interacting with long-wave radiation is removed. And so, you know, it just perturbs the outgoing long-wave radiation a lot less. And so no wonder that models as a group underestimate the long-wave direct radiative effect efficiency and therefore the direct radiative effect. So let's get at what this is then. You know, let's constrain the long-wave direct radiative effect so we can figure out how that has changed and what the radiative forcing from that is. We can do this with a fairly simple analytical model of, you know, the radiative transfer in the situation and what the perturbation is at the top of the atmosphere. We can come up with an equation for this then, for the change in the outgoing long-wave radiation as a function of the dust in the atmospheric column. I'm not going to go over this this equation, but I'll tell you what's in it. It depends on the dust aerosol optical depth, of course, in the long-wave spectrum, the single scattering albedo in the long-wave spectrum, so what fraction of interactions result in scattering versus absorption, the fraction of scattering that results in downscatter, like I said, that's around 15% or so, the surface temperature, this determines the amount of radiation coming from the surface, and the dust layer temperature, and it's really the difference between those two that determines how effective the absorption is, because the dust layer temperature determines the radiation by the dust layer, and it's the difference of that with what's coming from the surface that causes the long wave top of atmosphere radiative effect due to absorption. And the perturbation to the long wave radiation budget by dust is mitigated by absorption above the dust layer. Right? If there's a lot of absorption above the dust layer by water vapor, for instance, then that mitigates the perturbation to the outgoing long-wave radiation, because, you know, a lot of the radiation that's being scattered or absorbed by dust wouldn't make it to outer space anyways, because it'd be absorbed by this water vapor. Okay, so we have this equation for what the top of atmosphere outgoing long-wave radiation, what the perturbation of dust to that is. Now we need data to drive this analytical model. We're going to use, of course, this dustcom product that my group developed. This is a four-dimensional climatology in terms of season, latitude, longitude, and height. Of course, we need to figure out what the interactions are with the radiation. For this, we use optical properties drawn from 6 different data sets. We use reanalysis meteorology from MERA2 to figure out the temperature and humidity profiles, and also ozone. We use a radiative transfer model to calculate the absorption by the atmosphere, which modulates the dust radiative effects. And, you know, the schematics I showed you here, of course, for clear sky, we need to account for the effects of clouds, which are quite important. That's very complicated to do in this analytical model. So instead, we use the ratio of the whole sky to the clear sky direct radiative effect from this group of models, from the ensemble of 6 different models. Okay, now if we use this data-driven model to predict what the long-wave direct radiative effect efficiency is, we get a much better result than for models, because this includes supercoarse dust and includes long-wave scattering, right? So we get a larger effect. You can see the colors here now roughly match the colors of the data. And if we put this now on the scatter plot, you can see that this bottom-up analytical model pretty much captures the magnitude and a lot of the spread in the data. So it's very encouraging. And again, this is a bottom-up model, and it's now agreeing with these top-down measurements. So that's really great. So we can then use this data-driven analytical model to calculate what is the global long-wave direct radiative effect. Right, so we take this map, essentially, we integrate it, and we add the 4 different seasons, and we have the perturbation to the outgoing long-wave radiation by dust in the modern climate system. Right, again, that's not the radiative forcing. The radiative forcing would be the change in that perturbation from pre-industrial to the modern period. So So we get around 1/4 of a watt per square meter, and this is much larger than what the models had. So these models underestimate the long-wave direct radiative effect by a factor of 2. We surveyed the literature. We got around 21 published model results of what the global long-wave direct radiative effect is in these models, and this is around 0.13 watts per square meter, so about half. That is not a surprise because these models, by and large, do not have nearly enough supercoarse dust, and we can calculate per size range now what the contribution is. And supercoarse dust accounts for around 20% of the long-wave direct radiative effect, so it's important to include. And even more importantly, these models neglect scattering, and the scattering is very effective at creating perturbation to the outgoing long-wave radiation because of this 15% probability of scattering an upward traveling photon down. And so scattering accounts for over half of the long-wave direct radiative effect. So most models do not account for this, and therefore this really drives the underestimation of the long-wave direct radiative effect by models. If we now add this to the shortwave, so the shortwave direct radiative effect is around half a watt per square meter. We add the two together, and we get that the total net dust direct radiative effect is a cooling of around 1/4 of a watt per square meter. So half a watt per square meter of cooling by shortwave, offset by 1/4 of a watt per square meter of warming by long-wave interactions, leaving around 1/4 of a watt per square meter of cooling. So if you now combine these two results, right, we have this 55% increase in dust since the pre-industrial period, meaning that around 1/3 of dust in a modern climate system wasn't there in the pre-industrial times, with this result that the direct radiative effect of dust is around 1/4 of a watt per square meter. So if you take dust entirely out of the Earth system, that changes the radiation budget by about 1/4 of a watt per square meter through direct interactions. So since 1/3 of that is new since pre-industrial, the perturbation, the change in the direct radiative effect is around -0.09 or -0.1 watts per square meter. So it's been the direct radiative forcing due to dust. Now, to put that into context, the total greenhouse gas warming is around 40 times that at 3.8 watts per square meter, and the aerosol cooling is around 10 times that, around -1 watts per square meter. So it's an important contribution to include. Of course, it's still sulfate cooling, aerosol cooling is still going to be largest, but this can be, especially in regional scale, can be quite important to understanding how climate has changed and how it will change in the future. So to put it then on this graph, right, from the 6th assessment report, we have around -0.1 watts per square meter of cooling here from dust, and that translates to a surface cooling of around -0.06 degrees centigrade. In other words, if it hadn't been for dust cooling, we might have already blown through the Paris Agreement. Is another way of saying it. So this is important to include. Dust has counted around 3 ± 5% of the surface temperature increase due to greenhouse warming, and this omission has slightly biased climate sensitivity constraints, slightly biased climate sensitivity low because of this. And of course, there's a global climate picture, but on the regional basis, this cooling is about an order of magnitude larger. So very important to include when thinking of the climates of, say, the Dust Belt, Northern Africa, Middle East, Central Asia. Okay, that brings me to our conclusions then. I think one of the most important findings is dust has increased substantially, around 50%, and models do not account for this. So there's a big push to put this into models now. That's facilitated by this dust emission inventory that my group has developed from 1850 through 2000. We have a paper in review right now, actually extending this to 2023 using satellite data. We put this into modern climate models with active aerosol cycles. We get a radiative forcing due to dust of around -0.2 watts per square meter. We think this is overestimated because models underestimate the heating from long-wave interactions, and correcting this, we get a direct dust radiative forcing of around -0.1 watts per square meter. And that has offset around 3 ± 5% of the surface temperature warming due to greenhouse gases. And that is my seminar. So I'd love to take any questions.
Oh, thank you so much, Jasper, and it was an interesting presentation. So
Thank
we will
you.
now open the floor for questions. So if anyone have any questions, please feel free to unmute yourself or drop it in the chat. Yeah, I think it's Franco.
Thank you, Sai. Thank you, Jasper, very much for. I want to thank you very much for giving us this seminar, and also to do it at 7 in the morning, which is not the nicest time.
Yeah,
I also want to thank the students for organizing it, and this is really great that they are so interested in research and organize these webinars. And I wanted to ask a couple of questions. Of course, I don't want to monopolize the questions. So if other people have questions, please prioritize them. It's about the shortcomings of the models. So rightly so, you say that the models do not do not represent the increase of dust. And you were mentioning that to put it in, but I don't know, I haven't understood if you're thinking to put in what you have, the constraint, the observational constraint that you have, or
right.
whether it's, yes, but my question is what's missing in terms of processes in these models for this? Is it probably the interaction with human activities? I don't know. And the second question is about the relationship between radiative forcing and particle size distribution, which you mentioned. And we know that models are constrained mainly using aerosol optical depth. And I was wondering whether to ensure that models have a correct representation of the size distribution, we need to think of new observational constraints to the models. I don't know if you can comment on this.
Yeah, great. Lots of really great questions. Yeah, what processes are missing from models? I think that's a really important question. We don't know exactly what's missing. It's quite likely that the way that changes in the Earth's surface are described in models is missing some really important things. For instance, the shrinking of lakes is not in there. Effects of agriculture on dust is partially in there in terms of changes in LAI, but like removal of crust, all these things are not in models. It's not really clear which of these is most important. It's also possible that the change in climate itself, right, has driven changes in dust. For instance, this peak that we see in the 80s, that might be a forced response to, it might be because of aerosol cooling that peaked in the 80s, pushing the IGCC south, and that driving drought, and that causing more emissions. These are all questions that have been, I think, flowing around the literature. We don't have definitive answers to them yet, unfortunately. So I think that's a really exciting area for study, I would say. Okay, and then you asked about the size distribution, right? What we need to have in models. I think the size, that's this is a really great field, lots of mysteries, right? We don't really know why the supercoarse dust is so heavily underestimated in models. Partially, certainly, this is because not enough is being emitted, but even when you emit a lot more, the stuff just falls out really fast in most models. It's kind of mysterious. Partially, it's that the dust is very spherical, and that keeps the dust aloft a little bit longer, but it doesn't really get you that really strong increase you need in order to match measurements. Another factor is that there's turbulence there might be turbulence, for instance, in the Saharan air layer. And that's often not included in models that can increase the lifetime of dust. Those are the main process. There's been some suggestion that it's electric fields keeping these particles aloft. I haven't seen as much evidence for that, but that's certainly not in models. In terms of measurements we need for that, that's a really great question. I think having like Lagrangian measurements, like a balloon floating in the Saharan air layer, that'd be my ideal approach for trying to tease apart what the processes are that's happening within a dust plume that might be keeping these particles aloft.
Thank you.
Thank you, Franco.
I don't want to ask more questions because I want other people to ask questions.
Okay, we have one question in chat. It's from Ralph. He's asking, so what do you assume for dust optical short and long wave properties? And can you assess how much uncertainty this might contribute to the net dust forcing, or is that just a detail?
Excellent, that's great. Yeah, so for the short wave, we asked the models to use optical properties that were obtained by Claudia Di Biagio in a laboratory setting. This is, I think, now sort of the default in the literature. For the long wave, it was kind of complicated because there's not nearly as many measurements, and they're quite varied. And so we've collected 6 different data sets on this, and we cycled through them essentially. So we did a bootstrap approach, and then we randomly chose for each bootstrap iteration which optical properties we used. And then from that, we get we calculate the disagreement with the constraints on the observational constraints on the direct radiative effect efficiency, and then we retained the simulations that were within the observational spread, essentially, which were actually something like half of the total bootstrap iterations. So and that allowed us to use the observations to fairly narrowly constrain what the long wave direct radiative effect efficiency is, while accounting for that we don't know exactly what the long wave optical properties are. I hope that sort of answered the question.
Okay, so the next question is from Sakshi. She was wondering about the CMIPS peak climb tuned 2x dust experiments. So how helpful they are in terms of the radiative forcing estimates and the climate response to it in comparison to the observed changes in the dust aerosol concentration. In short, she wants to know how realistic they are, and also any comments on the dust role on aerosol cloud interaction.
Great, lots of great questions. So the 2 times dust simulations, I believe those are for the future. Yeah, we don't know how dust will change in the future. The dust has decreased since the 80s. You saw that in the, maybe I can pull this back up. So there's been a decrease in dust since the 80s, right? There was this peak in the 80s. We've since looked at satellite data, and I think it's my next slide. This is from a paper that's in review right now, and we see much more gradual but continuing decline, around 10% total from 2003 to 2023. So in the more recent past, dust has actually decreased. We don't really know how dust will change in the future. It's highly sensitive to how models predict precipitation will change in the future. And for instance, for like the Sahara, some models predict actually a strong increase in precipitation, some a further drying. We don't really know which is truth, although most models predict an increase. So the 2 times dust for the future, I think a doubling of dust is probably not realistic for the future. If I had to put money on it, I think probably dust would decrease in the future, because that's what we see in the paleo records, right? That when there's warmer periods, generally dust decreases. But these experiments are very useful for understanding, the effect of increased dust or decreased dust by extension on climate. I think there was a question about cloud interactions. Those are really important. We haven't, in the review paper, we give a range for these. There's a lot of uncertainty in those because there's very limited process understanding, and not many models have produced results for these. But roughly speaking, dust interactions with warm clouds are thought not to be as important, because it's overwhelmed by other aerosols, because dust is important in terms of mass of aerosol, but not so much in terms of number. So in terms of cloud condensation nuclei, it's not nearly as important as other aerosol species, but it's really critical for cold clouds, for mixed phase clouds, cirrus clouds. And there we have very divergent results in terms of whether it's warming or cooling.
Thank you. So next we have a question in the chat, and Kenneth is also there, but I think Fernando is the one first who asked. So it's like Fernando is asking, given that airborne measurements are crucial for constraining atmospheric models, what implications do you foresee from the recent decisions to shut down Farm Airborne Research Facility?
We shut down, sorry, Farm, what is
It's
the
a
word?
FAM. It's FAM, FAAM, FAM.
Oh, I see. Okay. Well, I didn't know that. That is unfortunate. Yeah, I mean, we rely heavily on these airborne campaigns to constrain, especially processes, optical properties. So that's very unfortunate. I'm sorry to hear that. Yeah.
So I think it's Kenneth.
Thank you for your nice presentation. Personally, I'm working on dust particle shape and orientation. I may have missed that in your presentation, but I was just simply wondering, how did you actually represent the aspherical shapes in your models? I guess you know that they are like approaches from Gus Steiger and recent approaches by Saito and Young, I think a couple of years ago. I mean, given that basically, you know, if you get like a whole distribution, it's far from spherical. So I was wondering if you implemented that, and if not, how would you do it, and which effects you would expect to see?
Yeah, it's a great question. Yeah, so the shape is important for two reasons. One is it affects the settling speed, and two, it affects the optical properties. So for the optical properties, we asked models to include refractive indexes within a certain range based on laboratory constraints, laboratory data. We did not prescribe the effects of shape on the optical properties. Effects of shape on optical properties are generally thought to be small. The main effect is that it affects the mass extinction efficiency. But because the dust cycle is constrained by the total optical depth, if you account for shape, you change the mass extinction efficiency, you change how much mass is needed to explain that optical depth, but you don't change the total extinction of radiation. And so if models adjust the shape, calculate new optical properties, and then constrain the dust cycle with optical depth constraints, the change in the radiative effects are pretty small, 5 to 10%. Not that it's not important, but it's overwhelmed, I'd say, by uncertainty in the imaginary index of refraction. So I think the shape is very important when you look at the angular distribution of the radiation. For remote sensing, it'll be really important, and possibly for the settling processes. And also now that we're nailing down the optical properties of dust more, there's this EMIT mission, right, from NASA, measuring the mineralogy of soils. We get a much better constraint on the optical properties. It would make sense to incorporate the effect of shape more in the optical properties.
I see. Thank you.
It's kind of.
Okay, now we have two more questions remaining. So it's from Legrande. Sorry if my pronunciation is wrong. I think it's Legrande. And all dust has the same properties, or is in the point of doing the provenance work to get at the mineralogy and potentially diverse radiative properties? And also, how does your GRIS result compare with recent dust provenance work there over the last millennium?
Great. Yeah, exactly. So these models, by and large, did not include regionally varying mineralogy. That's sort of some models. Let me back up. One of the models did. The other models did not. So that's still to be included for sure. Yeah. And that will certainly affect especially the regional distribution of radiative forcing. And there's indications from the mineralogy, the constraints of mineralogy from EMIT, that the dust is in models is too absorbing. So that also needs to be included in models, and would probably make the radiative forcing of dust more cooling, and it would change the regional distribution of it a little bit. I'm sorry, the last question, could you repeat that?
Also, how does your GRIS result compare with recent dust provenance work there over the last millennium?
What is GRIS?
Greenland ice sheet.
I'm sorry, say again.
Greenland ice sheet.
Oh, the Greenland ice sheet.
Yes.
That's great. Yeah, exactly. So the Greenland ice sheet, the provenance data generally shows that most of the dust is coming from East Asia, although I understand there's been some controversy in that there's maybe more indications now that some of it's coming from North Africa. So the DustCom product shows generally too much dust there, especially from North America. So that indicates that there's too much dust coming from North America in these models. It doesn't matter so much for the global dust cycle because North America is just a few percent, but for the interpreting what's happening, where the deposition of dust from to the Greenland ice sheet is coming from, it's showing a discrepancy there. Yeah.
Okay, then we have one more question. I think most of the people have this same question. So it's what is in general, what is the level of variations of chemical compositions of dust from different regions and hence their shortwave and long-wave radiative forcing properties?
So how does shortwave and long-wave radiative forcing differ per region? The balance between them? Did I understand it correctly?
Yeah, like what is the level of variations of chemical composition of dust from different regions? And hence how their shortwave and long-wave radiative properties are changing.
So how the differences in dust mineralogy, how that affects across the different regions, the shortwave and long-wave interactions. Is that right? Okay. That's a great question. For the long-wave, we don't have as good constraints, but I think the laboratory data shows that there's less variability than for the shortwave. I don't have a really great sense, to be honest, of how the optical properties differ per source region. Generally, the Sahel is thought to have more absorbing dust. Australia, more absorbing dust. Beyond that, I haven't seen the latest results out of EMIT yet. At least they're not top of my mind. So I'm sorry, I can't answer that question very well. I think for the long wave, the mineralogy importance of mineralogy is less because the effect of size is more dominant in the optical properties, and I think we have less of a sense. We have fewer measurements of how that varies. The mineralogy that's important for the long wave interactions.
Okay, thank you. So I think next question is from Simanti.
Hello, thank you for such a nice presentation.
Welcome.
And I also work with dust modeling. I have just started working with dust modeling, and I was going through a few of your extensive works. So I have two trivial questions. First, so I'm working with WRF Chem. This model does not account for anthropogenic aerosols. We wanted
Right.
to ask the models and the ensemble that you used, do they account for the anthropogenic aerosols or they do not?
That's right. So
Inside the model.
That's right. Yeah. So for the maybe go back. The models in the let's see. Sorry, I have to go back a few slides. In the DERF here. So yeah, these account for anthropogenic aerosols prescribed by the CMIP6 protocols.
And my second question is, there are two extensive papers on constraining dust for the global dust cycle. I just wanted to know a few challenges you face because this seemed like a very elaborative and comprehensive work.
So what are the challenges in general in dust in the field?
Just in general, not in the field, just to produce those constraint and those statistics that you have on those papers.
Oh, great. Yeah. I think the really big one, I would say, is that it's really hard to infer what happened in the past. And our main source of data for this are the deposition records. But in order to link the deposition to what's in the atmosphere, right, we need to assume that essentially the emission hasn't changed. And that's a really big assumption. And that could cause large errors. It helps that we have, like 19, 20 different deposition records, so that, if there's changes in transport patterns, dust, if it's decreased in one area, it would decrease in another in principle. But I think that causes large, we should interpret the results with caution. The error bars on the results are lower bound. Yeah.
Thank you very much.
Thank you.
So we have one more question in the chat. It's do your results depend on assumptions about the vertical distribution of the dust layer, or are they relatively intensive to height?
Yeah, that's really great. So the vertical distribution matters quite a bit. For the shortwave interactions, it determines whether the dust is above or below the cloud, which greatly affects the net perturbation. For the long-wave interaction, the height determines the temperature of the dust, and thus the temperature difference with the surface. So it's quite important. So generally, the top of aperture direct radiative effect for in the long-wave spectrum will scale approximately linearly with height of the dust layer. So yeah, that is actually quite important. In the constraints that I showed, the vertical distribution is obtained from models, from an ensemble of models. We know models struggle getting the vertical distribution correct. So that's and we could implement constraints on this from spaceborne LiDAR. That would further improve the constraint on the long wave interactions. But just to reiterate, because the let me see if I can find the result again. Because the spread in the observational constraints, on how much the perturbation to the energy budget is per unit of optical depth by dust is fairly narrow. It probably wouldn't affect the answer very much to include constraints on the vertical distribution. If that makes sense, because it's already in pretty good agreement.
Okay. So next we have one more question. So it's, do you know if there is any indication that dust aerosol forcing will be included in the next IPCC report?
Yeah, there are indications. There's several multi-model experiments that are using the emission inventory, and those are part of the CMIP7 experiments. So there are indications. I can't say yet, but certainly there are people that think it should be included, and my hope is it will be. Yeah.
Okay, thank you. So, is there any other questions? If not, we are already past the time. So thank you once again, Jasper, for sharing your expertise with us today and for starting your morning so early to be here. And thank you everyone for joining us. And we hope to see you all the next one. Have a great rest of your day. Thank you, everyone.
Yeah, everyone. Appreciate it.
Thank you very much, Jasper and everyone.
Thank you.
Thank you very
Thanks a
much.
lot for
Thank
joining
you.
this webinar.
Amazing talk.
Thanks, Jasper.
Thanks, everyone.